Here it is, the last section. We're in the last chapter, and then this is the last section we're going to talk about. We've already seen how to work with power series. Okay, these are series of functions. Okay, something a little different from our series of real numbers. Okay, we know how to construct them, work with some of their basic constructions like the geometric series and how to manipulate new from old. Okay, and we know how to determine the intervals of convergence, radius of convergence, which the punchline is a ratio test. But now we're going to come across a remarkable theorem that tells us how to express any smooth enough function as a power series. And this is the only Taylor that really matters now. This is the Taylor series. So what does the theorem say? Well, really, it's just a definition here. So we're going to first assume that I have a function f that I want to approximate on some interval, okay? And I want to approximate this around x equals a, okay? Then I can write the so-called Taylor series for this function around the point a as follows. It is an infinite sum where we have coefficients that are the nth derivative of the function evaluated at a, scaled down by n factorial, so we divide by n factorial. And then we're talking about powers of x minus a, okay? And so what does this look like? So the constant term is just the function at the point, f of a. Then we have the derivative at a times x minus a. The second derivative at a over 2 factorial gives x minus a squared, and so on. So this is our construction for the Taylor series, okay? And in fact, we can write this in a slightly different way here. If you like, you can also express this as follows. Let's get here. We can also express this as f of x equals, okay, this infinite sum here, which I'll go ahead and change the color here, okay? The coefficients here, in fact, let's just do it in red. We have the Taylor coefficients Cn, which are these guys right here. These are the Taylor coefficients Cn. And then we have the powers around the point x minus a to the n. Okay, so this is any power series, as we saw before. This is from n equals 0 to infinity. And then here we have the relationship that the Taylor coefficients Cn are precisely those derivatives evaluated at a divided by n factorial. And so what do you need for a Taylor series? You just need evaluations of the function at the derivatives. Now, of course, you have to assume that all the derivatives exist, okay? So-called C infinity function, or any function that's sufficiently smooth. Now, we have this extra point here that if we are centering at 0, okay, let's go ahead and write this here. If we're centering at 0, it's known as the Maclaurin series of f, okay? So for the Maclaurin series, okay, so if I do a Maclaurin expansion, it's the same idea, except now instead of going at around some arbitrary point A, we're constraining this to now be around x equals 0, and so the center of the series is a equals 0. And so how do we do this? So let's ask ourselves, how do we construct this thing? Let's do this in this blue color. So we compute the derivatives. Okay, and by the way, in case you're not familiar, whenever we have that superscript of n in the parentheses there, that's just saying the nth derivative, because writing, say, 12 primes gets a little messy here. Okay, so let's make a remark there. This thing here is the nth derivative. Okay, so we're going to find the derivatives. That's the first step. The second step, okay, is to evaluate the nth derivative at the point A, and then divide by n factorial. And then that tells you exactly how to construct the Taylor series. Now, the key here, okay, so here, the key is to find the pattern. And this is where you have to do a bit of exploration. Okay, so we have a nice little framework to construct these Taylor expansions. Okay, so this is our working definition for the Taylor series. And it's not as bad as you think it is. A lot of our nice functions, right, e to the x, sine x, cosine x, even arctan, we can get nice Taylor expansions. Okay, and we can just get that from taking these derivatives. Now, some functions, like say tangent, secant, natural log, may require a bit of work. Some of these functions may require some extra tools, but for now, we're going to go ahead and talk about how to construct these basic Taylor expansions, and then how we can also construct new ones from old. And for that, I'll see you in the next one.